Kia ora, Year 12. In this video, I'm going to start going over the binomial theorem, which is something you worked on quite a bit in AS, and we extend it in A level. So let's go right back to the start, because some of you have probably forgotten some of it. We're going to start with doing a really simple expansion that we can do just from Year 9 algebra. So let's look at how we can expand x plus y squared, and we're going to work up from this to much more complicated things. So expanding this gives me x squared plus xy plus xy plus y squared. All right, so we get x squared plus 2xy plus y squared. So you're probably going, why is she starting with something that basic? This is a bit silly. What I want you to start thinking about is this combination here has got a coefficient of 2. And the key to understanding the binomial theorem is to start thinking about what these coefficients mean. So in this case, the first term, the x squared, happens when we take an x from here and an x from here. And there's only one way to do that. Now let's see if I can erase. No, I can't erase just the yellow bit. Okay, I'll put the yellow bit back on. So there's one of those. And the y squared happens when I get this y from this bracket and when I choose this y from this bracket. So there's only one way for that to happen. So there's an invisible coefficient there of 1. Now what about the 2xy? Well, that's happening because I can either take the y from the first one and the x from the second one, or I can get an xy combo when I'm choosing the x from the first one and the y from the second one. So there are two ways for that to happen. Okay. The next thing we're going to look at is what happens when we move up a notch and expand x plus y cubed. So we can write that out as follows. Now usually when we first do this, when we're doing slightly harder than Year 9 algebra, we get into a pattern where we take one term and then we expand these back to. We've already done that and we get x squared plus 2xy plus y squared. Then we go again and keep on expanding. So we're going to get x cubed plus 2x squared y plus xy squared. And now we do the same thing with all of the y terms. So altogether we get 6 terms, and then we can combine some like terms. 2xy squared plus y cubed. So when we work like this, we're not really thinking in a binomial theorem way. What we're doing is we're just looking for our like terms, and we see that we've got 2x squared y plus another x squared y gives me 3x squared y. Here we've got an xy squared and a 2xy squared, so we get 3xy squared plus a y cubed. But now I want to go back to start thinking how we did with choosing things. So let's think again about how many ways are there to choose x, x, and x, because that's going to generate this x cubed term. Well, to do that, I have to have the x from this one, the x from this one, and the x from this one. So there's only one way that that can happen, right? So that's 1 x cubed. And the same idea happens for the y cubed. There's only one way for that to happen. But what about this one here, x squared y? How many ways are there to get that? Well, that can happen when I do any one of the following things. I can have x, x, and y, x, y, and x, y, x, and x. So that's 3 things. Okay, so looking at it circled up here, I could get the x here, the x here, and the y here, or the x, the y, and the x, and so on. So that's where the 3 comes from. Now, hopefully you'll remember that we can get a really fast way of figuring out those coefficients, but it's important to think about the meaning, which is about choosing a certain number of things from a group of objects. So Pascal's triangle is the really nice thing that you learnt last year about how to get these coefficients. Whoops. Pascal's triangle works by taking the 2 coefficients from above and adding them together. So that is pretty powerful, because it means if I said to you, I want you to go and find me x plus y to the power of 5, then you don't have to do this thing anymore. You just have to go down to the 5th row of Pascal's triangle, which is not too bad, and use these as the coefficients with our pattern. So we'll start and we'll have all x's in those brackets. So that's only 1x to the power of 5. Then we're going to have 5 ways to get 4 x's and 1 y. And we're going to have 10 ways to get 3 x's and 2 y's. And there's a really nice symmetry that you can see that lets us finish that off quickly. And there's lots of things that you start to notice when you work on problems like this. Obviously, because we've got, this is to the power of 5, these indices always add up to 5. All right, and there's an invisible one there, so the same thing here. It's just something that's always worth checking. So that's all good. So Pascal's triangle lets us figure out binomial expansions. And sometimes, even when you've learnt the other way, it's more efficient just to race in and do Pascal's triangle. But what if I said to you, we need to figure out x plus y to the power of 23, or even just the first 5 terms of it. So we really don't want to have to do this all the way down to the 23rd row, right? That gets very, very painful. So we're now going to start talking about a thing called a combination. And a combination is just Pascal's triangle, but it's a formula that will let me skip all the way down to any part of it. Okay, so a combination is how many ways are there to pick R things out of N things. And that's when the order doesn't matter. Now, sometimes you'll see them written like this, NCR, right? And we can get this as follows. We have n factorial in the numerator, and down here we have r factorial times n minus r factorial. And n factorial is just n times n minus 1 all the way down till we get to 1. Okay, I find that when students first see this combinations formula, they think it's absolutely horrible and they're never going to want to use it, but it's actually quite easy to do. Okay, so heading on to the next page, you can think of Pascal's triangle as just a whole bunch of those combinations, right? So let's look at how we can make it work for bigger ones. Right, so if we wanted to figure out, start with one that looks horrible, 15, choose 4. All right, so this is going to be one of the coefficients if I wanted to go all the way down to the 15th row of Pascal's triangle so that I could do an expansion of this form. So in the numerator, we just have 15 factorial, and in the denominator, we have 4 factorial times 11 factorial, right? So it's n factorial over r factorial times the difference in those two numbers. And if you play around with this a bit, you'll see that that means that that fits in with the symmetry, because 15 choose 4 is the same as choosing 11 objects from 15. Right, now what do we do with this? Well, a whole lot of stuff is going to disappear. 15 factorial is 15 times 14 and so on, down to 1. 4 factorial is 4 times 3 times 2 times 1, and then 11 factorial is 11 times 10 times 9 all the way down to 1. So if you think about that, a whole lot of stuff is going to cancel out. This bit up here matches this bit down there, right? So included in 15 factorial is 11 factorial. So we're left with this, 15 times 14 times 13 times 12 over 4 times 3 times 2 times 1. And from there we can do some nice simplifying. We can see, in this case anyway, we can't always, but here, 4 3s are the same as the 12, and we can simplify 14 over 2 as 7. So it gives me 15 times 7, so 105 times 13. So you'll probably grab your calculator for this, but I'm doing this in my head. So what's 105 times 13? Let's think. So it's 1050 plus 315, which gives me 1365. So that would be the coefficient 15, choose 4. So we know that one of the terms, if we did this expansion, well, the first one would be x to the power of 15. The next one would be 15x to the 14 y plus something we haven't figured out, plus something else. And then the next term in there would be 1365 x to the power of 11, y to the power of 4, and so on. Okay, so that's a very basic revision of combinations and how they work. Now I want you to have a go at a couple on your own. This first one, x plus y to the power of 7, is one that you can do either using Pascal's triangle or using combinations. And then the second one is one that I would just do with Pascal's triangle. Okay, on this page I've set up all of the combinations for the 7th row of Pascal's triangle, just to give us some practice in using the combinations. So 7 choose 0 means how many ways to get no objects out of 7. So that's always 1, right? Think of that as when we're trying to get all of the x's from the brackets, right? So we've got 7 brackets, we need to get x, x, x. There's only one way for that to happen, and at the same time we know that there's only one way to get this one down here. So those two are easy. Right, the next one, 7 choose 1, is also going to have a familiar pattern. So if you think about those 7 brackets, we want to say how many ways are there to get 1x and all the rest be y. So there will be 7 of those. But if we're doing it using the formula, we can see it as well. We have 7 factorial over 1 factorial, 6 factorial. And the 6 factorial part is hiding inside the 7 factorial part. So that all simplifies. So that's how we get 7 there. I'm just going to erase that bit for now. Now I'm probably going to run out of room here, as usual. So what about 7 choose 2? Well, 7 choose 2 is equal to 7 factorial over 2 factorial, 5 factorial. That cancels, some of that cancels out to give me 7 times 6 over 2 times 1. 7 choose 3 is 7 times 6 times 5 over 3 times 2 times 1, right? Because this 4 bit is a term that simplifies. Okay, so that goes. Now, 7 choose 4 is going to be 7 factorial over 4 factorial, 3 factorial, and that also is going to simplify to 7 times 6 times 5 over 3 times 2 times 1. And 7 choose 2 and 7 choose 5 are the same, so they're both going to equal 21. I should have simplified this down to show you that this will give you 35. This one will also equal 35. This one will be 7 and this will be 1. And if you're doing this with Pascal's triangle, you'll know that those numbers match up exactly. Okay, so we get 1, 7, 21, 35, 35, and so on. Okay, so then you can go on and you can do your expansion, but I'm running out of time, so I'm not going to do that. Okay, now the next question, the last one that I asked you to do, I also can't squeeze into this video. But the big idea in here is that you'll get your coefficients from Pascal's triangle. Right, so you're going to use the 4th row, and you're going to have this and this instead of your x and y. But I'll come back to that in the next part of the video as we build into some harder problems.